Today I'll be talking about the gauge problem in cosmology, but before that, as most of my friends know that I am quite a positive person, I always like to bring out the positive things from any situation. But even for a person like me to get positive things out of this whole pandemic scenario was quite difficult. However, it's true that this whole fiasco of lockdown and etc. has given us some very interesting things. For example, the webinars. And that's why nowadays I really enjoy joining webinars for very obvious reasons. And so therefore, I wish you all a very nice and happy rest and sweet dreams and everything. Okay, so coming back to the gauge problem in cosmology. By the way, this talk, when Momita told me to give a talk, I thought I'll actually target it towards our grad students and pre-grad students who will be working on cosmology from this year, or who are working and who will be working from next year. And so this talk is more pedagogical in that respect. So as you know, you take up any cosmology paper, recent cosmology paper about structure formation or gravitational lensing or G waves or anything, you will see these words just floating around those papers: gauge freedom, gauge invariance, frame independence. Then there are different types of gauge: harmonic gauge, transverse stressless gauge, so on and so forth. So the question is, what are these and how are they related with any cosmological perturbation? So actually that brings us to the cosmological perturbation theory. So let me try to give a very, very basic idea that what exactly is a cosmological perturbation theory. So let's start with absolutely a poor man's picture. Everybody knows what a extrapolation by Taylor expansion is. Well, I said it's a poor man's picture. Actually, any perturbation theory is some sort of expansion around a 0th order point. That means, to explain it properly, we know how a system works exactly at a point in parameter space, and we just want to extrapolate that around that point to see how the system works if we shift a little bit from that point in the parameter space, and that's exactly is any perturbation theory. So the same should be true for cosmological perturbation theory too. So what we do generally, we think of an absolutely idealized Friedman, Lemaitre, Robertson, Walker universe, which is towards my left in the picture. And everything, the energy density, pressure, if there is pressure, the Hubble, the curvature, I'll be denoting it by an overbar. And in the right side, this one is the real universe, which is definitely not homogeneous and isotropic. So it's a lumpy real universe, and all the quantities will be represented without any overbar. So what is our idea? Our idea is that from this idealized universe, there was a small perturbation in density, in other things, in the matter, in the gravitational perturbations, whatever, that created a lumpy universe, which is definitely different, but not much different from the idealized universe. So in other words, if the metric of the idealized universe is G over bar AB, and the metric of the realistic universe, which we stay in now, is GAB. So delta GAB, this small change in GAB will be given as the difference between these two. Similarly, delta mu will be given by the energy density as we measure now, subtracted with the idealized energy density. Okay, so far so good, but as soon as we define our perturbation theory in the usual sense like this, we come into problems. And what are the problems? The problems are that the measurements can only be done in our realistic universe. In other words, we don't have a Harry Potter wand that can say, okay, now let's make the universe absolutely homogeneous and isotropic. I'll take one measurement, and okay, now go back to the original position. I'll take another measurement, and then I'll subtract these two and see what is the perturbation. We cannot do that. And that's the important part in any perturbation theory, in any Taylor expansion. It's very important to know the value of the function at the point around which you are doing an expansion. For example, if you want to extrapolate how the sine function looks like, you must know the value of the function and the value of its derivative at x equals 0, say. But in this case, we are doing a perturbation, but we have no idea about what the realistic universe's value is, because there is no data possible for idealized universe. So very obvious, the system is underdetermined. So going back one step, you can see we can only know GAB and mu. We don't know delta GAB, and therefore we don't know what is G over bar AB or mu over bar. So it is an underdetermined system. And all we know is the perturbations is very small in some suitable sense, but that's all. That's all we know. So let me give you a very simple example, a toy example, that how it can create a problem. Let in a class there is a twin Sheldon Cooper, okay? And in some units, say, the measured density at a given space-time point is 37.73. Now, the first Sheldon Cooper will be very happy. He will say, this is absolutely fantastic because 37 is my number, 73 is the mirror image of my number, and so the background is 37 and the perturbation is 0.73. That's brilliant. But now the Sheldon Cooper 2 will say, oh, no, not at all. The background must be 37.37. That's my number written twice with a decimal point exactly in between. And the perturbation is 0.36, which is the square of the ratio of the first twin prime numbers. So penny, it must be the second one, right? So now my question is, do we have any mechanism by which we can resolve this fight, that who is right? The answer is capital N and capital O. Why? So let me exactly explain that what exactly we are doing when we are saying we are perturbing. So this is in the left, this is my idealized universe, and in my right, there's a lumpy universe. And as I showed you, we are taking a difference, but we cannot do any algebra on two different spaces. So whenever we are taking a difference of, say, the metric or the energy density, it must be on the same space. The values must be on the same space, same manifold, same space-time manifold. So what exactly we are doing is, we are doing a mapping from the idealized space to the lumpy space, and let this mapping be mapping phi. And then on the lumpy space, what we are doing is we are taking the difference of the original measured value with the mapped value, which is going from S bar to S. Now, what is this mapping? This mapping is entirely arbitrary. It is done by hand. The reason being that we don't know any measurement because of for the idealized universe. So the choice of this map is absolutely arbitrary, within certain very broad restrictions, of course, that the mapping should preserve causality. that we cannot travel in time. It has to be causal map. The map has to preserve energy conditions, so on and so forth. But these are very broad restrictions. Within this broad restriction, whatever map we do is fine. So what happened in the Sheldon-Cooper case was both were doing a separate map from the idealized universe to the real universe. And then what happens is the perturbations are dependent on how the map is chosen. And also, whenever we are doing a map between two manifolds, of course, my X differential geometry students will immediately remember my course. Whenever we are doing a mapping between two manifolds, the local coordinates also gets mapped with the same mapping. Therefore, this mapping is most of the time expressed in terms of coordinate choice. And this is exactly what is called gauge freedom. Why freedom? Means we can do any mapping possible within some arbitrary constraint from the idealized universe to the real lumpy universe. And that's my freedom. I can do my own mapping, Matt can do his own mapping, Sudan can do his own mapping, and it's all fine. But then the problem is we have to say these are the results subject to this mapping. So that is the important point. Okay, so this is a nice picture from George's paper. In the right is the idealized FRW model. You can see the constant time surfaces are exactly smooth. And I am mapping those smooth surface into the smooth surface in S, whereas the gray lumpy surface is the actual lumpy universe. So what we do is we take the difference between that lumpy surface and the smooth surface, and that gives us the perturbation value. But again, this is entirely dependent on the mapping phi. Now here comes another point, which is called gauge transformation. What is a gauge transformation? The gauge transformation is, by definition, the change in mapping keeping the background fixed. So I keep the whole story fixed, my background universe and my lumpy universe. All I'm doing is changing my mapping. And this actually changes everything regarding the perturbation theory. For example, a covariant scalar that does not change under any coordinate transformation, that's the reason they're called scalars, may change under gauge transformations. So as I said, I mean, for example, the example I gave about 2 Sheldon Cooper. The mapping, one mapping was that the energy density at that point was 37, and by another mapping it was 37.37. So you see a scalar is actually getting changed because of the change in mapping. So this is what Bardeen writes in his famous paper where he defined this whole thing about the gauge transformation and gauge invariance, that a gauge transformation changes the point in the background space-time corresponding to the point in the physical space-time. Thus, even if a quantity is a scalar under coordinate transformation, the value of the perturbation in the quantity will not be invariant. That is very important under gauge transformations if the quantity is non-zero and position dependent in the background. So this is a very important point to take home, that covariance and gauge invariance are two entirely different things. A quantity can be covariant, but it may not be gauge invariant. Okay. So how do we specify this mapping phi or specify a gauge? So any complete specification of a gauge must have 4 important properties. First is we need to map families of world lines with families of world lines. For example, in an idealized universe, the natural families of world lines will be the along the fluid flow lines, and we'll map these families of world lines to the families of world lines in the lumpy universe. So And the natural mapping may be from fluid flow lines to fluid flow lines, or sometimes it may be easier to map the fluid flow lines of the ideal universe to the hypersurface orthogonal world lines in the lumpy universe, so on and so forth. It depends on what exactly we are trying to look at. So that is mapping families to families. Now we also have to map specific correspondence between given world lines. That means which observer in the idealized universe corresponds to which observer in the lumpy universe. Now, in case of when the idealized universe is FRW, for example, then all observers are the same, so it doesn't matter which observer you are actually mapping into. But for general mapping, one must specify the specific correspondence between the given world lines. Similarly, we must map the families of space-like hypersurfaces. That means we must say which hypersurfaces are constant time hypersurfaces in both these scenarios, the idealized and realistic universe. And again, the fourth point is specific correspondence between this time surface. That means giving exact value. Okay, this is a constant time surface. I give this time surface the value of t equals 5, for example. So any complete description of a gauge must have these 4 properties. Now you can describe a gauge with lesser properties. For example, you can describe it with just 3 properties. Then there is a gauge freedom still available with you in your calculations, and you have to be very careful that any physical quantities you are trying to calculate, whether they are coming because of that great gauge freedom or not. So that is the main point. Okay, so this is again a pictorial representation of how do we do the mapping. So the choice of families of world lines, that is the A. So these are the families of the world lines. The mapping B says how one specific world line is mapped to another specific world line. Similarly, C is the family of space-like surfaces, and D is the choice of particular correspondence between surfaces from one family in the idealized universe to the one family in the realistic universe. Okay. Now I'll give you a very fun example of a very funny gauge, just to show that how we can use this mapping freedom to make things quite arbitrary. Now let's see, in the realistic universe, let Q be a point in the realistic universe, and gamma is the world line passing through Q. Now, since it's realistic and lumpy, of course, the exact constant density surfaces will not be the same as the constant density surface of an FRW spacetime. But what we can do is, around Q, we can just find the set of points with constant density exactly, and then make a hypersurface with those set of points. It will be space-like if the realistic universe is not much different from an FRW universe. And we find a constant density hypersurface around Q. And now what we do is, we consider these families of constant density hypersurface. So once we do that, we see delta mu, which is the difference of density between the idealized universe, the mapping of idealized universe and the real universe, will be only a function of time, because now we are dealing with constant density hypersurfaces around Q. Again, with our gauge freedom D, we can specify the density, energy density at a given hypersurface in a way that delta mu, which is the difference between the idealized density and observed density, is exactly 0 at that given hypersurface. We can do that. And then what Bardeen showed was that there is always, we can find a specific proper time for the point Q such that when the point evolves, the delta mu or the change in energy density remains zero as we go further in time. In other words, what we have done is, this is very interesting, we have found a mapping from the idealized universe to a realistic universe which has no density perturbation altogether. Isn't that funny? But why don't we use it? It's such a nice gauge that we did a mapping where there is no density perturbation from the idealized universe and the realistic universe. But then obviously you will immediately ask that how is that possible? The realistic universe has lumpy densities. So where does those inhomogeneities come in? Well, the inhomogeneity is now coming in from the proper time. As I just said, for a point Q, we can define a proper time which makes the delta mu zero throughout. But from other points, we'll have to define different proper times to make the delta mu zero. So in other words, although we have density to be constant in the mapping, the proper time between 2 points in the realistic universe will now be different, and that's exactly where the inhomogeneities come in. So in philosophy of life, this phenomena is actually called law of conservation of crap. You can only shift crap from one point to another, you can never get rid of it. So this is one brilliant example for that. So this is a very interesting example of a zero density perturbation gauge, and yeah. But you see, it doesn't help us much as far as our analysis is concerned. So how do we fix the gauges? There's some very natural gauge what we can think of. So one possibility is to define clearly the equivalent proper time gauges, equivalent proper time between two models, and use this to completely specify the time function and fix the gauge. And the obvious choice in this case is to choose proper time from along the fluid flow lines from the Big Bang. So this is a quite clean solution to the problem. The only problem is, as Bardeen pointed out in his seminal paper, that since we are calculating the proper time from the Big Bang, this gauge is a non-local gauge. For example, what is the perturbation now won't be given by the measurement done now. We have to integrate our perturbation from now to in the past to the Big Bang, and that will give us the proper time. So in spite of this being a very clean solution, this is not helpful at all because it is non-local. Also, we can have gauges which flow orthonormal, that will take the orthonormal slices as constant time slice from our flow vector, time-like vector UA. However, this is possible if and only if there is no vorticity in the universe. But we know the fluid vorticity in the perturbed universe is definitely non-zero. So this strategy won't help much. And furthermore, it's also not very clear to how to assign specific value of time or density in this sort of gauge. So again, it's sort of a problematic gauge. Third is equivalent scalars. So we can map scalars, for example, the Hubble parameter in the idealized universe to the Hubble parameter in the lumpy universe, or just like I gave you the example of constant density perturbation, so on and so forth. Again, it's a nice gauge, but the problem is the information about special density fluctuation is coded in a very weird way. For example, in the constant density gauge, the information about the local inhomogeneity was coded in proper time, which is a bit absurd. So again, this is not a very, it can be used, but not a very helpful situation anyway. The most promising one is definitely which is spatial averaging, that you average out the energy perturbation in the lumpy universe and let that be the mapping from the idealized universe to the lumpy universe. So that is a very promising approach. But the problem of averaging is in GR, the average and the tensorial description doesn't commute. For example, calculation of Einstein tensor using an averaged metric is not the same as the average of Einstein tensor using a non-averaged metric. So they do not commute, and therefore the averaging is still an open problem as far as the cosmology is concerned, and still we don't know how to go about this. So now the question is, as we have seen that our result typically depends on this mapping.
Rituparno, can I ask you?
Yes, please.
This Krolak has done for this averaging thing.
Yes,
Krolak.
not only Krolak, there have been a lot of work on the averaging thing.
No, I was talking about Tolman 1D and this Jacques model.
Oh yeah. Not only Krolak, even our friend in Mexico, what's his name, Sussman. Sussman has a lot of work on that.
Yeah.
But the thing is, in a general sense, it's still not very clear that how do we take the average, because we take the average of a metric or we take the average of Einstein tensor. It's still not very conceptually clear. We can do a lot of things, definitely, but yeah. So thank you. So now the question is, everything depends on this mapping, as we have seen. But can we say something meaningful about this perturbation or the perturbed universe that do not depend on the gauge choice or the mapping? Now here comes a very interesting answer. The answer is yes. So these are called gauge invariant variables. Now what are gauge invariant variables? You see, in the idealized universe in our left hand side, which had everything, an idealized FRW. So in that idealized manifold, anything, any scalar, vector or tensor covariantly defined, they are the geometrical objects on manifold. And when we do a mapping between one manifold to other manifold, we actually map these geometrical objects, scalars, vectors and tensors from one manifold to the other manifold. Now what happens if a tensor, say a scalar, is 0 in one manifold? Then phi of 0 is of course a constant. Now phi 1 of 0 is a constant, phi 2 of 0 is another constant, phi 3 of 0 is another constant. So whatever mapping we are using is giving us some different constant that has nothing, that has no effect on the dynamics of the system. So what we are doing is we are just changing the baseline, that's all. The dynamics are remain the same. So in other words, any tensor, any covariantly defined tensor that is constant or vanishes in the background spacetime or in the ideal spacetime is by definition will be gauge invariant, because the gauge, the function phi, the mapping phi is acting on a constant and is giving a constant value, which is just a baseline change, that's all. So the only possibility for gauge invariant quantities in a tensor is a constant linear combination of products of Kronecker delta. This was given by Stewart and Walker lemma, a very important lemma. And so what is the take home moral of the story here? Anything that vanishes in the background, any covariantly defined tensor that vanishes in the background is by definition then by Stewart and Walker lemma will be gauge invariant. So how do we develop, knowing this lemma, how do we develop a gauge invariant perturbation theory? So there are actually two ways one can do it. The first one, which is very famous and oft used, is the Bardeen's metric based formalism. You take any paper on cosmological perturbation, the highest probability is they are using Bardeen's formalism. It's based on metric potentials. So I won't go there. Rather, I'll go to the second one, which is not so often used, but a very nice and geometrical semi-tetrad formalism, which is both covariant and gauge invariant. And this was developed by George Ellis, Marco Bruni, and Peter Dunsby when Peter was in his, when he was a postdoc in 1992, they worked in UCT and they developed it. So I'll just go into the second one and explain how do we actually develop a cosmological perturbation theory that is both covariant and gauge invariant. So for that, what we do is we use the 1+3 covariant formalism, and we consider a unit time-like vector, which can be the matter flow line. Of course, that is the most natural choice. And we do consider the projection tensors based on this vector. So basically, we are dividing the metric in the direction of the UA and orthogonal to UA. So similarly, we can decompose the 4 volume element to the usual 3 volume elements, so on and so forth. And then what are our kinematical variables? When we define a family of, say, time-like congruence, the obvious choice are the geometrical choices are the expansion. How is this congruent coming near each other or going apart from each other, which for Friedman-Robertson-Walker model is just 3 times the Hubble parameter. We have the shear, we have the vorticity. Similarly, we have the matter variables, the energy density, the mu is the energy density, QA is the heat flux, P is the pressure, and pi is the anisotropic stress. So all these are our kinematical variables. And now we want to use the geometric equation for these kinematical variables to find out how they evolve. Now, the obvious question you might ask is, where is the physics? Where is the Einstein's field equation coming in? Well, the physics is coming like this. So the Riemann tensor, as we all know, can be nicely divided into its trace and trace-free part. The trace is the Ricci tensor, and the trace-free part is the Wild tensor. Now it turns out, according to this little chubby cheeks boy, that the Ricci tensor is somewhat related to matter. So therefore, whenever there is Ricci tensor in the problem, we'll just change it into the matter variables, and that's how we incorporate the physics into it. So for example, we keep the Wild curvature variables as it is, the electric part and the magnetic part. And when we write the full Riemann tensor, what we do is, instead of writing the Ricci tensor, we use the matter part, mu, 3p, q, etc. So now we can use the usual Ricci identities. So we'll get a set of equations like this. We use the usual Bianchi identities doubly contracted, and we'll get the set of equations like this. Now you see, all these variables are covariantly defined. So now whatever is 0 in the background, by definition, they are becoming gauge invariant. So if the background is Friedman, Lemaitre, Robertson, Walker, FLRW, then all the Weyl curvature quantities, the shear, the vorticity, the heat flux, the anisotropic stress, everything is 0 in the background. So by definition, they are gauge invariant. We don't have to think about that. But now what about the quantities that are non-zero in the background? For example, energy density is non-zero in the background. Expansion, or which is 3 times the Hubble parameter, is definitely non-zero in the background. In a general background, the 3 Ricci scalar or the 3 curvature may not be 0. I'm not talking about especially flat Robertson Walker, so that may not be 0. So these are the background quantities. Now they are not gauge invariant when you map into the real universe. So what do we do? Now here we do a nice trick. So instead of these quantities, we define their 3-dimensional gradients of these quantities. For example, instead of mu, which is the energy density, we'll define the 3-dimensional gradient of mu divided by mu with the scale factor, and that will be my vector dA, curly dA. Now you can easily see that the curly dA is 0 in the background. In Robertson Walker, all the special gradients are 0. So these curly dA, curly LA, these are all gauge invariant quantities, and then we can extract the scalars from these gauge invariant quantities and special derivatives, and then we can write the field equations. I'm not going into details with these gauge invariant scalars. So just to give you an example, for dust when pressure is 0, this energy density, the measure of the energy density perturbation delta, which is the scalar perturbation of the energy density, has 2 modes. The growing modes goes as t to the power 2 by 3, and the decaying mode goes as t to the power minus, I cannot see it anyway. And similarly, the radiation, it's very similar. So in the long wavelength limit, we have the growing mode going as the time, and the decaying mode going as the inverse of time, and so on and so forth. So this calculation shows that actually the energy density perturbation is actually non-stable, and that's how the I'm sorry, that's how the structure forms in the universe. So this is exactly at par with the Bardeen's calculation, which was done in 1980 to show the structure formation. So this is just the gist of how do we do covariant and gauge invariant perturbations. So this is I like it very much because we are dealing with both covariance and gauge invariance simultaneously. So whatever we say doesn't depend on the gauges and doesn't depend on the coordinate system. So it's quite robust in that way. So I guess this is a nice time to stop here, and talking about the decaying mode. I'm keeping tab on this graph every day, and we are going on a decaying mode now. I sincerely wish we continue with the decaying mode so that instead of webinars, I can actually attend a seminar and sleep there. Thank you very much. Okay.
Okay, thanks a lot. So we'll take some questions. So if firstly, let's open it up for students specifically. If students have any questions, please go ahead. Yeah, Inge, will come to you, but I'm just giving chance for students if they want to ask any questions. Okay. Okay, I guess I don't see anything on the chat also. Okay, fine. So Inge, yeah, you can go ahead.
Okay, Ritu, first of all, masterpiece. Thanks very much for this very nice talk. My question is that when you say the if a quantity that is 0 at the background level, then it should be gauge invariant. Then how can I understand the three-dimensional matter power spectrum P of K is actually gauge dependent? So if it's synchronous gauge or it is Newtonian gauge, then it is different. On small k, on basically small wave number, which is large scale. So that are different.
Yes, I entirely agree with you. But what I said is any covariantly defined tensorial quantity that is 0 in background. The power spectrum is not a tensorial quantity, so it won't fall into that category.
Okay, I see. Then how do you explain the power spectrum for two gauges? One is a Newtonian gauge, the other is a synchronous gauge, that are not different for large K, which is a small scale, and small K, but quite different on large scale.
Okay, yeah. I am not going into the details of calculation. The thing is done like this. For example, in the gauge invariant way, what we do is we find the delta, which is the density perturbation in a gauge invariant form, and then we extract the info about the power spectrum with that delta. We cannot do it in general. We cannot solve the perturbation equation. So what we do is we break it into small wavelength limit and large wavelength limit, and then do the calculation on the power spectrum. So there are steps by steps involved. First, we define a gauge invariant quantity, write down the gauge invariant equation, try to solve it using the usual Fourier modes, and then go to the large wavelength limit or the small wavelength limit, and then calculate the power spectrum using that. And then, as you rightly said, in one wavelength limit, we see that the power spectrum does not depend on whether it's Newtonian or the other gauge asynchronous. In the other wavelength limit, it does depend. So that is a series of calculation involved in between.
Oh, thank you. Just another thing. So you show a number of interesting tests and figures in your talk. Are they from a particular paper, or that is your lecture notes?
That is the seminal paper on the gauge by Marco Bruni and George Ellis. It's called Ellis and Bruni. You can give it a search.
Okay, thank you. Yeah.
Okay, thanks, Sanjay. Any other questions? Yeah, Sudan?
Well, I don't want to go into depth of the subject, but just a mathematical idea of the frames that I used. I mean, the reason I'm asking this question is because nowadays in the world of modified gravity, there's people, when you devise some new idea, there's always some trade-off, you lose something. For example, the Gauss-Bonnet proposal is normally working in higher dimensions, but people are now running into lower dimensions, and there's a loss of some of the mathematics. For example, the Einstein frame has to be modified to the Jordan frame and that kind of thing. Did you read anything about that kind of stuff? Which is more physically reliable, the Jordan frame or the Einstein frame? The Jordan frame has got a scalar multiple of the Ricci scalar.
Yes.
Of
course, it's the Jordan frame, because the Jordan frame is the frame in which we live in. The Einstein frame is the conformal frames. And that's how, in fact, it started from the Brans-Dicke theory, basically. Any Brans-Dicke theory is same in the conformal frames, and that's how it started. But the realistic frame is the Jordan frame. So if you are trying to compare what is being measured with the data, you must do your calculation in the Jordan frame, because you are doing your measurement in the Jordan frame, not in the Einstein frame.
Good, thanks.